All right, so let's talk a little bit about titrations. I don't want to spend a lot of time on strong acid, strong base titrations because those are pretty easy to understand, but you have your axes, pH on the y-axis, OH equivalents on the x-axis, and again, depending on what's convenient, you can do this as volume of titrant, which would be sodium hydroxide. You could do it as moles of titrant, whatever's the most straightforward. But I like equivalence because then no matter what, you know that it's sort of independent of concentrations. So for instance, if you're titrating a strong acid with a strong base, undo that, you have the increase in pH, equivalence point, and then at that, that's a crappy line, 1.0 equivalent is when the moles of acid equal moles of base, and at that point, for a strong acid, strong base, the pH equals 7. All right, so let's instead go through the titration of a weak base or a weak acid with a strong base. All right, so the shape of this is, and we'll do the features afterward, you get a quick increase, and then it sort of flattens, you get your equivalence point, and then you have that. So still at that inflection point where the titration curve is at its steepest, that is one equivalent of titrant. Okay. And then the other features of that, if you go halfway across, 0.5 equivalents of titrant. What's special about that in the case of a weak acid titration? If half of it is titrated, that means that given that we're obeying the equilibrium of HA to H plus and A minus, what is special about going halfway across, and we start out with essentially 100% of this, and we add enough titrant to get half of it between that and that, what you have at that point is a situation where the pH equals the pKa, because the concentration of the weak acid will pretty much be the same as the concentration of the conjugate base. All right, so and again, a lot of this maps very, very well to buffers. But the types of problems you'll get with titrations might very well be to identify or calculate the pH of your solution given a certain addition of titrant. And it's important to sort of break this down into the different regions of the curve. So in the buffer zone, which is there's where you can use the Henderson-Hasselbalch equation. You don't have to use ice tables, and you'll be very happy. In the region just preceding that and just following it up to but not including the equivalence point, you're going to have to use ice tables. And so in the yellow, ice tables with, not the pKa, the Ka of your weak acid. In blue, you can use the HH, the Henderson-Hasselbalch equation, with pKa of your weak acid. And then in the region right at the equivalence point, you're also doing an ice table, but that is an ice table with the Kb value of your conjugate base. And I'm not going to go through tons of math here because we've done enough ice tables and you should know how to do them. But we'll just sort of show how this is set up. And then sort of finally, the top part of this curve is basically just an increasingly high quantity of titrant. And so we'll go through the sort of the general workflow of how to do all this. So let's start with the region of the Henderson-Hasselbalch equation, the buffer zone. And so basically, if you've got a certain quantity of strong acid, of weak acid initially in moles, and then you've going to have with that a quantity of your titrant, which is hydroxide in moles. And what's going to happen when you add titrant, regardless of where you are, is that your HA is going to get neutralized by that titrant to make water, which of course just gets added to your solvent. It just is your solvent. And then you're going to yield your conjugate base. And so until you reach the equivalence point, all along the titration curve, whether you're in the buffer zone or not, the speciation, so from here all the way up to here, is going to have, at the very beginning you have a very high concentration of HA, and you just solve that with an ice table. At the very end you have a predominance, 99+% of A minus, and you solve that with an ice table. And then everywhere in between you have some balance between the weak acid and its conjugate base. And the only difference between the blue shaded region and the yellow shaded regions is whether or not you can abandon the ice table and thus the quadratic equation, or whether you can go right to the Henderson-Hasselbalch equation and not have to do ice tables and quadratic equations. So, and that all has to do with how much A and HA you have after the titrant that you've added have neutralized it. And so if after adding titrant, you figure out what your sort of quantity of HA is versus your quantity of A is, of A minus, and go ahead and put that in your A to HA ratio. And if it is less than 0.1 or greater than 10, then you know you're not in the buffer zone, which means you have to do an ice table. And so in that case, you're ricing it up using in your initial row the concentrations, molar concentrations of A and HA that are there after you've done this sort of neutralization reaction, and your H plus will be set to 0 and you solve for your X, and then that's how you figure out your pH. If, however, when you figure out how much A and HA you have after you've done this sort of neutralization part, which is really just a limiting reaction type of problem, you react all of your OH minus with however much of this you need, and then however much is left is your HA quantity that you care about, and then however much titrant you added in moles becomes your quantity of A minus, and then you just have to figure out whether you're in the realm to do ice table or Henderson-Hasselbalch equation. So again, I don't want to run through the entirety of the ice table workflow because we've done that for a couple of chapters now, but needless to say, everything in here has to be in moles per liter, which means you need to, if you're putting stuff in moles initially, you need to get it back to concentrations. And the reason why you want to do it in moles is when you're doing this titration, you're actually adding volume. And so whatever the concentration of weak acid that you started with, say it was 100 millimolar, as you add titrant to it, 2 mils, 10 mils, whatever volume of titrant you add, you're inherently diluting that. So in order to calculate it accurately, you need to make sure your concentrations here are in moles per liter and not in moles. Okay. And then the Henderson-Hasselbalch version of this workflow, pH equals pKa plus log of A over HA if when you figured out your quantities of A and HA, and if you've then figured out that you are not in fact smaller than 0.1, if you're bigger than 0.1, or if you're smaller than 10, then you can plug in those values of A and HA after you've done the neutralization reaction on paper, and then plug in the pKa, the negative log of the Ka value, and just solve for the equilibrium pH. Okay, so that's using the Henderson-Hasselbalch equation as a shortcut of the equilibrium constant expression. So you're in the buffer zone, and if you are calculating the pH, yes, what you have there halfway through, or 3/8 of the way through, or 5/8 of the way through, yes, what you have there is a buffer. Even though it's not a buffer problem per se, we can still use the Henderson-Hasselbalch equation, which for the umpteenth time is nothing but a mathematical rearrangement of the equilibrium constant expression. And what you're doing is you're plugging in initial values of A and HA post-neutralization and approximating them for equilibrium values to solve for an equilibrium pH, given what we figured out with the math of this in lecture, that when you're in this ratio and your concentration is significantly high, that the value by which these concentrations change in the E row of an ice table will end up approximating to the same value as what they are in the I row. Okay? And so that's just a very straightforward application of the Henderson-Hasselbalch equation to calculate your pH. So again, you've got to go ice table. We need a new color here. Sure. Ice table here, and of course your A to HA ratio here will be less than 0.1, right? Because you've got mostly HA at the beginning. And then in this area, your A to HA ratio is going to be greater than 10, because you're going to have pretty much all conjugate base there. Here's your buffer zone, Henderson-Hasselbalch equation. So now let's talk about what to do at the equivalence point. And so when you've added one equivalent at equivalence point, so that means that the moles of HA are going to equal the moles of OH minus. That's the definition of the equivalence point, which means all of these will react quantitatively to give you water and A minus. So if you were titrating actually with sodium hydroxide, what you have at the equivalence point, sort of before you calculate equilibrium, is pretty much 100% sodium A, right? The sodium salt of your conjugate base. And if this were just given to you, what's the pH of sodium acetate or sodium hypochlorite or some other sodium salt of a weak acid, the salt of its conjugate base, the way you do that is to do the base hydrolysis reaction. So A minus plus H2O going to now HA and OH minus. And so you'd have to do a Rice table where you'd calculate the concentration of this, which would be the same number of moles of HA that you started with, now just divided by a new total volume. So it'll be somewhat more dilute than it was. Okay, this obviously doesn't play into account. We're going to call these 0. And then once you have your new diluted concentration, then it's just the standard Rice table workflow, minus x plus x plus x. Have a placeholder value in here, concentration, that's going to be a number, conc minus x, 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 and then you set this up as an equilibrium constant expression, x squared over that concentration minus x. Now this doesn't equal the Ka value, because what we've done here is not look at a acid dissociation equilibrium. We're looking at a base hydrolysis equilibrium, and so this is going to equal the Kb value. Now, how do we know what the Kb value is? Remember that Ka times Kb equals the Kw, which is 10 to the minus 14, right? So if you knew the Ka value or the pKa value of your weak acid, then you can get to the Ka by looking at that expression there. And so then you just do that quadratic equation, then you're all set. All right, so that's just going through some of the workflow for titration. The only other thing that we talked about in lecture was the speciation of a weak acid based on pH. Now this is much, much easier because other than phosphoric acid where you have to figure out which dissociation you're talking about, the first, second, or the third, we'll just sort of stick right here in this video about a monoprotic weak acid. And the only thing you need to use for this to find out the speciation, which is what is your amount of HA, what is your amount of A at a given pH, and you can just go right to the Henderson-Hasselbalch equation because you're plugging in an equilibrium pH and you'll spit out equilibrium A to HA ratio, and it does not need to be between 0.1 and 10. So I just want to make this point here that when you're plugging in equilibrium values, be it equilibrium pH or equilibrium A or HA, this whole 0.1 to 10 ratio constraint that we've been talking about doesn't apply. And the reason why, because the reason we've been using that constraint or specifying that as a constraint is when we want to plug in initial values for A and HA and approximate them as equilibrium values. The only time we can get away with that is if our A to HA ratio is greater than 0.1 and less than 10. Okay? When we're plugging in equilibrium values, we could have a 1,000,000 to 1 ratio. It doesn't matter. And so all you'd ever need, plus log of A over HA to speciate a weak acid based on pH. So that pH that we're talking about is what you'd plug in there. And then this is a constant. And then given that pair of values, you could spit out A, and HA is going to be some number you'd calculate, pH, or 10 to the, to be specific, 10 to the pH minus pKa, right? That'll be a number, and then if we're doing speciation as a percentage, you can set A plus HA equal to 100%. There's your second equation. If A and HA are a certain number of moles, you could set them to a number of moles or a concentration, whatever is appropriate for the question. But you'll need something here as your second equation to actually give you how much A you have, as quantities of the species. All right, so that's my quickie video on titration. Maybe not so quick, but let me know if you have any questions.